This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning. Yesterday we did the computation of equilibria and linearization. This is the first step in any analysis and design. This is also the first sort of mathematical tool that you learned in the subject. So we will keep moving more into mathematics as we go now. I will give a tutorial lecture today, in this afternoon. So if you have time, please turn up. I will be solving questions on linearization and equilibria. So that would be the plan for this afternoon. All right. So today we will continue talking about properties of models, or we will be manipulating linear models in particular. And we will talk about several basic properties of models. Two of these properties can be also applied to nonlinear systems, nonlinear models. But one of them, superposition principle, is special to linear systems. I mean, only linear systems possess this property. And the main topic of the whole lecture is really to arrive at the convolution equation, convolution representation of a linear system. Has anyone seen convolution before in signal systems or some of the subjects you did? Have you heard of the word convolution? Yeah? I see very timid nods. Okay, so yeah, so some of you have seen it. All right, so for some of you this will be a revision, right? But what I will do here is maybe what you haven't done in the past. I will derive the convolution equation using the basic properties of linear models. So what is convolution? Well, it's an equation that relates an input and output of a general linear system. So convolution representation is special to linear systems. Nonlinear systems do not have this sort of representation or property. And the main goal of today's lecture is to derive this equation. So what this equation says is, give me any input, u, I can calculate the output of this system using this equation. Now, note that in this equation there is this function g, which you may know or you may not know what it is. This function g really depends on the system itself. So this function g depends on your system. So you can think of this g, or convolution representation, and g itself, as the model of your linear system. Does anyone know what is the name of this function g? If you've seen convolution, you may have also talked about what g is. It is related to transfer function, but it is not a transfer function. Sorry? Okay, well, inverse Laplace transform of a transfer function would be equal to g. But then the question is, what is the inverse Laplace transform of the transfer function? Does anyone remember? Sorry? Impulse response, yes. So remember that we will cover Laplace transform a bit later, but the Laplace transform of an impulse signal, Dirac function, so it has infinite amplitude, infinitely short duration. and it has an area 1. So if you look at the sort of area that, like if you integrate this function, the integral is 1, right? So Dirac function is sort of a signal of infinite amplitude, infinitely short duration, right? Impulse response is the output of the system that you observe when you apply impulse to the input. So you apply impulse to the input, you observe the output, that's what G is. G is the impulse response of your system. So what does this say? This equation here says something very fundamental about linear systems. It says that the response of a linear system is completely determined by its impulse response. So, in other words, if I know the impulse response of the system, I know everything I need to know about the system. Because given any input, I can calculate any other output. So if I apply to my system sinusoidal input, I can calculate what is the sinusoidal response using this equation. What I use for this is impulse response. Always I use impulse response to calculate any other response to your system. So I like to use this analogy. So if you go on a first date, blind date, if you want to know everything about the person, you have to produce something like an impulse input. So you shock the system, you shock the person, and then you just sit and observe, right? Then you would learn if the person was linear. Obviously, nothing is linear, as we learned. But if the person was linear, right, that's all you needed to do. Apply impulse response and just sit and watch. And then you will be able to predict any other response. So if you give them any other input other than impulse, you will know how the person would behave, right? That's what the significance of this equation is. It is very related to Laplace transforms, transfer functions. You will see it has fundamental sort of importance and utility in analysis of linear systems. And what we want to do in this lecture is we want to derive this equation. So let's now, so this is just a motivation for what we're doing today. This is an outline. I'll first motivate things a bit more, and then I will go through several fundamental properties of linear time invariant models: causality, time invariance, linearity. And then we will derive this convolution equation by applying all of these properties above. All right? Okay. By the way, causality is something that applies also to other types of models, like nonlinear, infinite dimensional. So, but we will talk about it, use it here just for the linear models. All right. So, why do we go through these properties? Well, either implicitly or explicitly, these properties would be used throughout the subject. So it's useful to summarize them now, to understand what sort of models we will be dealing with. We will demonstrate consequences of these properties by deriving convolution representation. So mathematical consequence of all of these will be actually convolution equation, right? All right, so let's now introduce some abstract notation. So look, what I'm saying here is I will say that my system is a map that maps any input to any output. We saw that this is a possible abstract sort of definition of a system. Any input is mapped for some output. By the way, you can think of this phi as actually your convolution equation, because convolution equation takes any input and it allows you to calculate the output that corresponds to this input, right? So this system phi is a map that maps, signals, set of signals, input signals to set of output signals. So we do write this sort of abstractly. We say that y is equal to phi of u, but phi is not just a function. In the convolution case, it's a function. No, it's a function of a function, right? So it's an abstract representation that we use here. So using this abstract definition of a system, right, or model, we will next define causality, time invariance, and superposition principle. And then we will go on and derive the convolution equation. All right, so let's first talk about causality. In order to define causality, I need to define this. So first, let's concentrate on this. So what is this notation? I have a signal u, which is defined for all positive time, right? Think of u as a sinusoidal signal, or as a step signal, or an impulse signal, or it can be anything, really. So this signal u superscript tau denotes a signal that's exactly the same as u on the interval 0 to tau, and then we set it to 0 for any time larger than tau. Okay? Can everyone digest that? So basically, if I have a sinusoid, right, and I have a tau at a certain point, my signal u superscript tau is exactly the sinusoid up until this tau, and then we reset it to 0 for all future time. That's what this signal is. So let's see what causality is mathematically speaking. Causality is a property of a system that satisfies this equation for all tau and for all inputs u. So let's now unravel what this means. So what is the first part? Well, phi of u is my output. I remind you that we said, in this lecture, we will use this abstract representation of a system model. So set of inputs are mapped to sets of outputs using this mapping, phi. So phi of u is really my output y. So what does this mean then? Sorry. Oh, this is going... All right. So what does this mean? This means that I'm considering output of the system truncated in this way using this definition. So phi of u superscript tau is the output truncated, in this way. And what is this thing? Well, this is the output of the system with truncated input u, and then I truncate the output. Now, you may say, oh, why would you do this? Well, intuition behind causality is that future inputs do not affect current outputs. So what you would be doing in future to your system would not affect what the output is right now. And this is a mathematically strict way, or precise way of stating this property. Why? Well, look, this part here does include, this is the output of the system for input as on infinite time interval, right? But we are just truncating the output. So this basically potentially, you might have that the future values of input here would mess with what the current value of the output is. But it can't happen if actually when you truncate the input, right, and then apply that to the system and then truncate that output, then you would have that future inputs do not affect the current outputs. Let me present graphically what this means. So this is a nice graphical representation. So look, you have here, let's look at first what would be the response of a causal system. So what I have here, I apply to the system step input, right? And I record step out, the response to the step input, which is the step response. And then what I do is I'll consider everything on this shaded region. Now, the end of the shaded region you can think of as my tau, my test tau, right? I'm truncating at that point, right? And now I'm saying, well, the causal system would behave like this. If so note here that I am applying step input and it doesn't change for all time, after this point. So I start at 0 and then I step maybe to 1 and I keep it constant. And I record this output. Now the causal system would behave like this. If I change this input so that after tau it has a different value. But in the shaded region, this and this is exactly the same. Causal system would produce exactly the same output because the future change in input did not affect the current value of the output. Right? So note that, yes, the output will change after the shaded region, but within the shaded region, there is no change. Right? How about non-causal systems? Well, we do the same thing here, right? The experiment is the same, but note now that the output of the non-causal system would change as a result of future changes in the input. Right? So, can everyone follow what I'm saying? The future value change in the input affects current value of the output or past values of the output. So non-causal systems typically, they don't arise in nature. Unless in the movies, like Terminator, like Back to the Future. Actually, these movies mess with your mind, and they are so interesting because they mess with causality. Right? Go and kill Sarah Connor, right? Then future won't happen in the way it happened, right? But mathematically speaking, however, we can write some non-causal systems, right? Mathematically, we can write equations that are not causal. And I will present some examples, but physically, you cannot generate using physical elements like electrical circuits or mechanical systems. You cannot generate non-causal systems. You can generate something that looks close to it, but not exactly non-causal systems. So, look, differentiator is not a causal system. So we will talk about PID control, but whenever we talk about implementation of the D element, the differentiator, we would have to make it causal, right? Practically, you would have to change the D action in order to be able to implement it. There exists some non-causal sort of algorithms when you do, signal processing, etc. But this is sort of artificial. This is all mathematics. When we talk about physical things, you cannot really. Maybe there exists some other universe in Star Trek, or where there exist non-causal systems, but we don't know of them, right? We don't know of them. All right, so that's the first property. Let's look at time invariance. So here I will introduce something different, a different notation. Know that this notation says signal S subscript tau is this. Now what is this? Well, this is basically the same signal, but I changed the argument of signal by tau. Tau is constant. So what does this mean? Well, I'm shifting the signal, so it's the same signal, and I'm just shifting it by amount of tau. I'm translating it with time. That's what this notation means. So what's a time invariant system? Well, if I apply shifted input to the system, I would just obtain shifted output. So in other words, suppose I apply basically, I consider an experiment, right? An experiment, and I have my, pendulum. And I apply like an impulse force to it, and then I observe the experiment. Now, what is time invariant? What does time invariance mean? If I decide to repeat this experiment tomorrow, using exactly the same force, right, the output of the experiment would be exactly the same. Things have not changed, right? So time invariance means the system does not change, right? So that's that. And mathematically you can say, well, if I keep shifting my input in any way, the output would be just the shifted version of the output that I would have obtained by applying the same input without the shift, right? So that's what it means. In graphical representation, this is what you have. Well, if I apply a step signal like this and I observe the output, this is like the step response, and then I shift the step signal. So know that here this jump happens after this jump. Then the output will just be shifted version of this output here. And that's exactly what I was explaining earlier. If I repeat an experiment with exactly the same input, I will get exactly the same output tomorrow, day after tomorrow, in 1 year, in 10 years, etc. That's what time invariance means. Time invariance means the model doesn't change, right? Well, actually, all systems are slowly varying because they age, there is wear and tear, there's a lot of reasons why systems actually change. However, in many instances, if the change is very slow and the interval of time over which you consider the system is large, you know, and I mean sufficiently, there's sufficiently small variation during this time interval, you can approximate your system with a time invariant system. Right? So we are happy working with time invariant systems because, you know, during the operation of the system wouldn't change much. That's what it means, right? Know that Laplace transform cannot be used for time varying systems. So if we wanted to account for time variation, we wouldn't be able to use one of the most important tools in this subject. So we have to be happy with this approximation of true systems in order to use a lot of tools. Sometimes you need to take time variance into account. For instance, when you look at these rockets, there is a lot of fuel in the rocket that you need to use initially, and then, you know, they even sort of get rid of part of the sort of body of the rocket that contained fuel after a while. So mass of the rocket changes abruptly. And you know, I think I told you already, I was once stuck on a tarmac, and the pilot was talking about features of the airplane, and he was saying, well, this airplane is like 450 tons, but when we land in LA, it will be 150 tons. So mass of the aircraft would change dramatically, right? You know Newton's laws of motion, mass is there in the Newton's equations. So the mass would change like twofold. So you can't ignore that, right? Okay. So here is the last property that I want to talk about. It's the superposition principle. So you may have seen, or it's actually linearity. Sometimes it's a direct consequence of linearity, but sometimes people use it as if this is the same thing as linearity. What is superposition principle? Well, here we go. So if I apply to my system, you know, an input that looks like this, it's a linear combination of inputs U1 and U2. Then the output that I obtain would be a linear combination of the outputs to inputs U1 and U2. So what does this mean? It means that if I perform an experiment with U1 and I get phi of U1, that's the output to this experiment, U1, and then I perform another experiment with U2 and I get phi of U2, that's the result of the experiment, then I do not need to repeat experiment for an input which is now A1U1 plus A2U2. This is a third experiment. I do not need to repeat that experiment because if the system is linear, I know that the result of the experiment can be constructed from the first two experiments, where I got phi U1 from the first experiment, I got phi U2 from the second experiment, and I just combined them in the same way that the inputs were combined. It's just the scaling factors are the same. Okay? Are there any questions? I mean, sometimes this is difficult to digest. No? All right, so you can draw plots to sort of graphically represent in a similar way that I was doing before, try to represent superposition principle for yourself. Where did you see this? Well, if you are an electrical engineer or you did electrical circuits in some of your subjects, you may remember that if you want to calculate, let's say, current through a resistor, in a circuit that has multiple sources, voltage current sources, what you can do is you can turn off all sources but one. You turn them off, you consider another circuit where there's only one source, and then you calculate current due to that source. And then you consider, you know, another source, and then calculate the current due to that other source. And in the end, you just add all the currents you obtained. That's superposition principle. But this would only work for linear circuits. Often you go over this quickly. Only linear circuits would allow you to do this. Similarly, in linear mechanical systems, you can't calculate, let's say, motion or movement due to each force at a time and then calculate their total effect, etc. But linearity was crucial in all of these engineering approaches for analysis in mechanical systems or electrical circuits. And we just summarize it here abstractly because any linear system has it. It doesn't have to be mechanical system, it doesn't have to be electrical system, it can be thermodynamical system or fluid flow system. As long as it's linear, it will possess this superposition principle, right? It will possess this property, yeah. So superposition principle does not hold for nonlinear systems, right? Does not hold for nonlinear systems. And obviously, many properties of linear systems are derived from the superposition principle. Linearity of Laplace transform follows directly from superposition principle. Linearity of Fourier transform follows directly from superposition principle, right? So what is the linearity of Laplace transform? You have a sum of two signals. Laplace transform of a sum of two signals is the sum of Laplace transforms of these two signals individually, right? So you will have a lot of these things that you will use. Well, we also use transfer functions because you have to put in transfer functions to really talk about these things. But linear systems would have this property, always. So, all right. So now we are up for the most exciting part of the lecture, and I'm just checking what the time is. Okay, so I think we have enough time. I want to just stop here and just ask if you have any question about any of the properties we covered. Yep.
If I have a non-linear system and I apply the linearization, can I do the superposition?
Yes, and then it's only valid locally around the equilibrium where you linearized. And it's approximation. So approximately, if you can linearize a system, then locally around an equilibrium, approximately superposition holds. But obviously, in order to do linearization, you have to have that your nonlinear model is differentiable. If it's not differentiable at a given point, you can't write the linearization. You have to use more complex tools to write an approximation of such a nonlinear system. So smooth differentiability of the model is important for linearization, right? But if you do have that property, yes, locally and approximately, because note in linearization we neglected higher order terms, right? So these higher order terms in the true nonlinear systems are still there. So strictly speaking, superposition does not hold exactly, but approximately, if you are close to the equilibrium, these higher order terms are neglected, and approximately you have that it applies. Good question. Thanks. Any other questions? Okay. Let's now embark on the derivation of convolution equation. In order to do this, I need to introduce some terminology. So I need to introduce step response. I already mentioned it in several lectures. Step response is defined in the following way. When you apply a unit step function, so what's a unit step function? It's 0 for negative time, and it's equal to 1 for positive time. So in room temperature example, if you set your temperature, if it was, let's say, 0, right, and you set it to some value, let's say 1 degree, right, then you have a step function. So that's and you keep it like that forever. Now, what's a step response? Step response is what you observe at the output of your system when you apply step input to it. Unit step response would be different for every different system. You know, some systems might oscillate when you apply step response. Some people may just sort of asymptotically converge to their steady state value and stay there. There are many different possible responses that you can observe when you apply step input to the system. What sort of response you observe depends on the system itself, right? Now, impulse response is the output of the system when I apply impulse to the input. What's the impulse? Impulse is a signal that has infinitely large amplitude. It's 0 for negative time, and it has infinite amplitude over a time interval that is infinitesimally small. And then it's 0 for all other times. So it's really like you kick your system and you just stop and you don't do anything. But you kick it with an amplitude that's infinitely large. That's an impulse input. And impulse response is what you observe at the output when you apply an impulse to the input. So is everyone comfortable with these two? Step response is what you see when you apply step. Impulse response is what you see at the output when you apply impulse to the input. Yeah? All right. So what we want to show is that a causal linear time invariant input-output map is completely characterized by its unit step or impulse response. In other words, we will prove that we can write the system input-output relationship using convolution. And we saw that in convolution there is impulse response. This function g was the impulse response of the system. So that's what we want to prove. So we will do this using time invariance and linearity. Now, this is where mathematics kicks in, and I will go slowly, but please stop me. I will let you to verify some of the steps on your own. I would concentrate on explaining intuition behind this proof, right? And all the mathematics you can go and verify the details yourself. So what I'm doing here is the following. I'm saying, all right, I want to, if you remember in convolution representation, I could write output as the convolution of input with its impulse response, with the system's impulse response. I want to derive this equation. But I'm saying now, okay, let me calculate what the output of the system is when I have an arbitrary input. All right, I have an arbitrary input. So what is given here in this picture is an arbitrary input, and that's the blue curve. So I picked an arbitrary input, okay? Now, this arbitrary input is a bit hard to deal with directly. So what I will do is I will assume that this blue function is continuous, like sufficiently smooth, so there is no problems there. And then I would approximate that blue signal using the red staircase-like signal. You have done this in Riemann integration, right? When you were integrating, arbitrary functions and you were calculating Riemann integral, you were sort of approximating it maybe by a step-like function like this, right? Now, what's interesting about this red function is that this red function can be written, right, in the following way. So note, I have here u at t0. That's the value of blue function at time t0. And then the red signal would be really saying, well, I keep that for a while. So basically, this says I scale a unit step function. Zeta is the unit step function. And I just scale it with a value ut0, right? Now, what is this here? Well, all of this is basically saying you can actually write the red function as a sum of pulses, and pulses are scaled by the values of u, the blue function, at certain points. But what are pulses? Every pulse can be written as a difference of two shifted step signals. So let me just maybe draw this. I don't usually use the board so people can, see it, see everything on recordings, but here I think it's important. So note, can everyone see this? So if I have a step signal like this, and I subtract from it a step signal that is shifted in time, and it looks like this, what do I get? Well, the value of this and this is the same, it's just negative. So I get a signal that looks like this. And then it's 0 for all time. Right? Can everyone see that? So what I can do then, I can say, well, I can multiply lots of such pulses. Each pulse is a difference of two shifted step signals, like a difference of two shifted step signals, and I will scale them with values of u at t0, u at t1. So what is u at t1? It is the value of the blue function at t1. What is ut2? It's the value of u at t2, etc. You can check that you can rewrite the red curve in this way, right? Where note that these zetas are now, look, there is t minus tn. This is basically saying that I'm shifting the step signal by the value tn. When we talked about time invariance, we were shifting signals. That's what this means, right? So what I will be doing now, I will be using this approximation of u, this u tilde, instead of u, right? I will use u tilde instead of u, and that would approximate the input u to the system, right? But then as these time instances, tn, get closer and closer together, in the limit I will have that this u tilde really tends to u, right? But in the meantime, I will just use u tilde to derive some useful equations, right? In order to derive the convolution equation. So we introduce these h sub tau. They are basically the shifted versions of the step signals, and we need them to generate these pulses, right? Then I rewrite this, I write u tilde as an approximation of the blue signal. So this is my red signal u tilde. And what I'm considering now, I'm considering the response of the system due to the red signal u tilde, the approximation of u. So I want to write that down. Well, what is this? Well, note that the input now, u tilde, is a sum of scaled inputs. I would use linearity here. Because what would be the output? It would be the sum of the outputs to the corresponding signals. I can also I can take scaling factors outside because of the superposition principle. So what I get is that the response of the system, y tilde, so this guy, due to u tilde, can be written in this way. But note now that I have here, step responses, either shifted in time or not shifted in time. And they are scaled by appropriate values that come from the u tilde signal. I use superposition principle here, right? Now, you can rewrite all of this in this way. So this is, I will leave it, we are running out of time. I will leave it as an exercise because I would like to get to the end of this. But the intuition is clear. We approximated u by u tilde. We are calculating y tilde. At this step, we use linearity. And moreover, we use time invariance because, to write the response in this way, shifted values of so the output to shifted values of input is really the same as shifted values of the output. So that's why I have here, this equation. So linearity and time invariance were used at this step. So if you rewrite this equation in this way, what you can do is the following. I can just now multiply and divide this equation by Tn plus 1 minus Tn. Why am I doing this? Well, note now since I'm dividing this thing by Tn plus 1 minus Tn, I'm getting something here that looks very similar to a derivative of function. What is the function on top? That's the step response, right? So basically, if I let Tn plus 1 minus Tn go closer and closer together, I actually get the derivative of the step function, right? But it can be shown, what is the derivative of the step function? You can show it is actually the response to the impulse, right? Why is this? I can think about the input to the system as the pulse of unit value divided by this time interval which goes to 0. So I'm dividing 1 by 0. So that's the input to my system. Well, what is that? Well, that's the impulse. So basically, as I let this thing to go to 0, it is the derivative of the step response, but that's actually the impulse response. And then if I let everything else go to 0, and I consider that sum that I presented earlier, well, the sum would converge to the integral from 0 to t. We are converting sum to an integral. This thing here actually converges to the shifted value of the impulse response. This g is basically the impulse response. This just goes to u tau, u at that time, and this tends to d tau, infinitesimally small change of time. And what you get is this. You get exactly what we started out to prove. So you have that y tilde then would tend to y, right? And y, can be written in this way, right? As we let these time intervals shrink. So what we've just done, we've proven convolution equation by using linearity or superposition principle and time invariance. Now, you may not have seen this derivation before, but I feel it's very useful for understanding of lots of material that comes later. Okay. So, are there any questions at this stage?
Do you expect us to prove it?
I can't hear.
Do you expect us to prove it?
Do I expect you to prove it? Actually, my expectations are rather low. But you would be marked based on displayed knowledge, right? So it depends on what sort of mark you want. Obviously, the deeper you understand the subject, the better the outcome, right? Mm-hmm. Any other questions? So note that what we've done in this lecture, we showed that we can represent a linear time invariant model always in this form. In the previous lecture yesterday, we were talking about different kind of models. We were talking about these models that involve lots of derivatives of inputs and outputs, differential equations. So differential equation is one way to represent your system. Convolution is another way to represent your system. Now, each of these different representations lead to a different type of tools, mathematical tools that can be used for dealing with your system, analysis and design tools. That's why we are very interested in going from one model to another. We will learn how to go from convolution to a transfer function representation, for instance, using Laplace transforms. And then you would see that using Laplace transforms, you can really do a lot of analysis and design, which is extremely useful. But convolution and Laplace transform are very compatible. Why? We will show later that a Laplace transform of the convolution of two signals is the product of the Laplace transforms of the two signals themselves. So basically, Laplace transform of this integral is basically Laplace transform of g times Laplace transform of u. So if I take Laplace transform of y and Laplace transform of all of this, I will get that Laplace transform of y is equal to Laplace transform of g times Laplace transform of u. That leads naturally to the definition of transfer function, because we will see that the transfer function is really Laplace transform of the impulse response, right? So everything fits together, right? And this is a very useful, tool, if you want, which we will, go back to on a number of occasions throughout the subject. All right. So look, what we today did was we looked at formal definitions of causality, time invariance, superposition. Just to remind you, causality means that future inputs do not affect current and past outputs. So future doesn't affect present and past, right? That's what causality means. Time invariance means that if I repeat the same experiment today or tomorrow with the same input, I will obtain the same output. That's what time invariance is. The model, the system doesn't change over time, right? Linearity or superposition means that, the linear sort of combination of inputs will produce linear combination of the outputs, which were responses to these inputs, right? And then we also derive this convolution model. So note that convolution model is a consequence of these basic properties, right? Now, because in nonlinear systems superposition doesn't hold, then you cannot represent, we cannot have convolution representation. There are generalizations of convolution for nonlinear systems, but it is not uniformly, it is not universally applicable. Maybe for some classes of systems you can write things that are generalizing convolution equation, but convolution itself doesn't hold. All right, that's all I wanted to say. If there are any questions, I'll take them. If not, yep. You are talking about workshops, not tutorials. Workshop, right? So, yeah. So workshops, the first workshop would be Simulink. Sort of you need to familiarize yourself with Simulink. It's workshop 0. So some people would have it tomorrow. So people whose workshops are on Friday, they start tomorrow. And it's just a familiarization. You have to learn how to use Simulink. There should be already on LMS, some material for workshop 0. Yeah. It's not marked, by the way. I can't hear that. Tutorial today, 2:15. I think it's the Wright Theater. Yeah. So you can find it on LMS. Just check it, but it's 2:15. Yeah. All right, thank you very much. I'll see you this afternoon then.
Yeah, Alicia?
Yeah.
Yeah.
Pasti.
Okay, so